so I get a 1 there. And if you do not have 1s on the main diagonal, it's pretty easy to fix that. You just need to divide by the coefficient that's on the main diagonal. Okay, so by dividing the last equation by 2, this is what I get. And now here's my triangular or row echelon form. Easy to solve. Z is 2. Take that, plug it back in, get a y. And this is exactly the same example that I showed you earlier where I did the back substitution for you. Okay, and here you take z, put it in there, take y, put it in there, and you get an x. And if I remember right, well, let's do it because I don't remember. So z is equal to 2, and then I get y plus 6 equals 5, which gives me y plus negative 1. Take these and put it in equation 1. I get x plus 2 plus 6 equals 9, so x equals 1. So my solution is 1 comma negative 1 comma 2. This is my solution. Okay, and let's make sure that the solution works. So you should really always go and check to see if it's working. And what I mean by that is I need to go back in the original system of equations, okay, which is this one here, and make sure that if I plug these numbers in here, it works. Okay, so if I take the first equation, I get 1 plus 2 plus 6 equals 9. Yep. The next one would be minus 1 minus 3 equals negative 4. Yep. And then the third one would be 2 plus 5 plus 10 equals 17. And wow, it's working. So always follow up with this step where you're going to check your answers and make sure that you're not smoking. Okay, it's a good practice in that. Okay, the next concept is about consistent and inconsistent. I kind of mentioned this term to you in 7.2. 7.3, we need it formally. Again, go back to page 497. View the definition of consistent and inconsistent, and let's work on this example. Okay. So I'm going to pause here for a minute, let you get this done. All right. So what I want to do is I want to use algebraic processes to see if the system is consistent, and if it's consistent, is it dependent or independent. Okay. And I'm going to use elementary row operations. So let me go snip this guy. And so I'm starting out with these linear equations. I want to try and put it in triangular form. So the first thing I'm trying to do is make this a 0, and I'm doing it by following this step. Okay. So again, let me just tell you that if you can't do this quite in your head, so what this step means that I'm going to take 4 times equation 1, add it to 2, and put it into equation 2, which means equations 1 and 3 will be unchanged. These 2 will be unchanged, as can be seen. If you can't do this in your head, do it on the side like I told you earlier. Okay, so I'll just show you what I mean by that. And so I get negative 4x plus 12y plus 4z equals 16. Okay. And equation 2 is 4x minus 2y minus 5z equals negative 7. Okay. This should be negative 16. Okay, that should be negative 16. So if I add these two, if I add those two, that cancels. This gives me 10y. This gives me minus z equals minus 23 right there. Okay. So again, if you can't do the process in your head, just work it out on the side and keep this all in one consistent area. Okay, you can use this on the side. So you might want to really split your page up along a column. These problems cannot be done in 1 or 2 lines. Okay, they will probably take a page or more. So I would suggest you divide your page into half, do your fair work on the left hand side and your sketch work on the right hand side. Okay, so now that I've got my system as this, I'm going to take this step to get here, And you probably can't see what I'm saying, but let me show you what I'm trying to do. Okay. Wait a minute. That was step 1. I got this as my result, and so I want system from here to there. So I have this system. I'm doing this move on it to get here. Okay, and I'm not going to go through the details on this move. I've done that enough times for you to follow. So if I make that move, this is my resulting system. Okay. Well, if you take a look at, for a minute, if you take a look at the last two equations, the left-hand sides are the same, but the right-hand sides are not the same. Okay, the right-hand sides are not the same. So clearly that can't be. Okay, clearly there's something wrong. So this system is called an inconsistent system. Okay, it's inconsistent because there are no solutions. You can't have 10y minus z equals negative 23 and 10y minus z is equal to 4 as well. That's impossible, and therefore the system is inconsistent. Okay. All right, so there are no solutions, in other words. Okay, so if you go back to page 497, remember consistent says at least one solution. So there are no solutions, and therefore the system is inconsistent. Okay, concept of, square and non-square systems. So there are some definitions that I want you to go over. I'll pause here for a minute. Again, these definitions are in the book, and I would suggest that if you're not getting it in here, take a look at your textbook and read that. Okay, so what we've done so far are what are called square systems. That is, the number of equations and the number of variables were the same. So in the past couple of examples that we've done, we've had 3 variables and 3 equations. So the system kind of looks like it's square. Okay, square. We can quickly kind of show you that. So this would be like, x plus 2y minus 3z equals 2. 2x minus y plus z equals 1, and minus x minus y minus z equals negative 2. So this is a square system. It's got 3 variables, x, y, and z, and 3 equations. So it kind of gives you a picture of looking square. Well, you can get systems that are non-square, okay, and there are 2 cases for it, okay. One is the case where the number of variables is more than the number of equations, okay, and that's called an underdetermined system, and I'll explain what I mean by that. Okay, so for example, you can have a system